then they're going to have to, don't do that, don't do it already.
So what's your name?
Oh, right, yeah, okay, excuse me. My name is Bryce Virgin. I'm going to go ahead and resume a talk on algebraic geometry that I began in the spring last semester. I gave 2 talks before, and I spent most of the time discussing classical algebraic geometry, or at least the setup, the playground in which that field begins its investigation. So that's varieties over fields. And now I want to talk about, and I spent all that time building up to the construction of a variety. To understand that, I first have to tell us all about ring spaces.
So it was recording, but like I ran out of space, so I had to delete.
Oh no.
Now it's recording.
Okay. Should I start
No,
any
no,
of
you're
that?
fine.
Okay. All right, good. So ring spaces. So a ring space is a topological space. So where X is a topological space, and F is a sheaf of rings, which I will go ahead and define for everybody. Is a sheaf of rings on X. So that means that for all open sets, there is a ring. And when I say ring in this talk, I'll always mean a commutative ring with unity. So forgive me if I don't say those words ever again, but I mean that every single time. So this belongs to the category of rings. Every single one of these FUs is a ring. And then for all inclusions of open sets into other open sets, so
this ring isn't commutative.
it is commutative. Yeah, that's why I said I'm not going to mention the fact that they're commutative and have unity, but every time I say ring, I just mean commutative with unity. So yeah, so if I have exactly, or to every open set I associate this ring. That's what this F is supposed to be. You can think of it, it's not just associating rings to individual open sets, but it also has one extra component, because remember, I'm not saying it, but this is a functor on the category of open sets on a topological space. So these are the objects in the category, the open sets, but there's also these morphisms, the inclusions of open sets into other open sets. For every single one of these, I get a restriction, so it's...
It says some subset of rings. Is it supposed to be elements of rings?
Oh, you're totally right, sorry. Yeah, belongs to the category of rings, thank you. That I just stopped writing things for whatever reason, appreciate it. So yeah, and then whenever I have a restriction, or rather, whenever I have an inclusion of open sets into another, I can always restrict elements from the larger open sets ring to the smaller open sets ring. And I'm going to go ahead and write this down. Goes VU. It technically doesn't matter as long as I stick to the same convention all throughout. Okay, so we have these restrictions, and they have the property that if I have a triple inclusion, or a double inclusion actually, so U included in V included in W, then I gotta make sure I do this right. I do this wrong every single time I try to write it down. So the one that we start in, the one that we start in is here. So I'm going to go W here and U here. This one's got to start here. It's got to go V. This one's got to go V. U. Okay. So what it means to restrict from a large set, open set, down to a small open set, if there is some intermediate, is exactly the same as restricting down to that intermediate open set and then restricting from the intermediate open set down to the smallest open set. It makes no difference. So this altogether makes this F a pre-sheaf of rings. Now, the thing that makes it a sheaf is if for all open covers, so open with X equals the union of all these open sets, such that there is also an attendant collection of what we call local sections on each one of these opens. So for every single one of these open sets, I have a section belonging to the ring associated to that open set. And furthermore, for all ij, I can go ahead and I start in either ui or uj, and then I restrict down to their intersection. And act this on fi. It'll be the same if I took the j element. So ui cap. So this is like the premier example of this is just taking a collection of continuous functions on the open sets of a topological space, and then asking that on the restrictions of the elements of the cover, those functions agree. So in that case, these restriction morphisms would be actually just subset restriction of a function, and we would be saying that on the overlaps of the elements of the open cover, all the different continuous functions are coinciding. That would allow us, if we were talking about continuous functions, to glue all those functions up together onto a continuous function on the entire space. And similarly, a sheaf is a sheaf if there exists a unique f on the entire space such that the restriction, I started there, start at x, go to ui. Ui, x, restriction of f to each one of the individual cover elements is exactly the section, the local section for that cover element. So this is the idea that sheaf not only has information for every open set of a topological space, that's what this association of rings to open sets does, but if I have a compatible family of elements from these open sets covering, and I actually could have done this more generally. It doesn't have to be the entire space X. It can be any open subset of the space. So I probably should modify that. But that's what makes a sheaf, not just local information at every patch, but I can patch compatible bits of information together into something global. Sheaves encode the ability to pass from local to global in this way. All right, so that's all a ring space is. It's a topological space together with a sheaf of rings. So now there's one more property that I need to add. Here, let me get this. One more thing that I need here, because we don't just care about arbitrary ring spaces. We want them to have an extra property so that we can think of the sheaf of rings on them as coordinate functions, in a sense. It's functions into a nice space. Even if they aren't actually those things, we'd like to be able to use that analogy in places. And in order to do that, we're going to need to discuss something called the stalk of a sheaf. So if we got our ring space, we define the stalk for a point x in the following way. It's going to consist of equivalence classes of elements. Whoops. So U, V, open subsets of x such that. So elements of local sections for open cover elements that contain our points. So we'll start with these guys. Both contain x. And for any of these open sets, the equivalence class members for our stalk here will be sections of the rings associated open sets. And we'll say that any one of these guys determines the exact same equivalence class of such sections. So this guy. If there exists another open set, W, contained in the intersection, so U intersect V, such that the restrictions of my cover elements, so this is now down to W, U, F, coincide on that open set, W, V, G. There. So I've got this stalk. Prior to taking the quotient that makes it into what it is, I've just got all of this, the union of all of these these rings for all of these open sets that contain X. And then I turn it into equivalence classes. I turn it into a quotient by saying that two of these elements are the same if I can zoom in far enough that they become equal. So these now, they determine the same germ, we would say, in the stalk. And now the stalk is the collection of all of these germs of sections at the point. And we can induce a ring structure on this stalk by just using the ring structure on individual elements here. You define products by zooming down to an open set on which two sections both exist. Okay, so that's what the stalk of a ring space is. It encodes the information that that sheaf has at that point of a space. And now, in order to have our ring spaces be sensible,
So the stalk is the equivalent class?
yes, the stalk is the set of equivalence classes. Prior to taking that quotient, I just take the union of all of these. So let me even actually write it out very, very explicitly. So first, this equality is going to be illegitimate at first, and then I'll write the quotient, and then it will be legitimate. So we take a union over all the open sets that contain X. So that's what it means, that like every single one of these sections, FG, no matter which open set contained that point, every single one of them determines a germ. But then that thing is too large. In order to bring it down to the size that we need it to, we say that any two elements in here, which will always be of these forms, they'll be equivalent if they look the same if you zoom in far enough. Okay. So, and that would mean you would just go ahead and quotient by exactly that equivalence relation that I've got written there. So now a locally ringed space, which is what we're working up towards here. Okay, so that's going to be a ring space with the property that every single one of its stalks, such that for all X in our point, every single one of its stalks is what we call a local ring. F of X is a local ring, which, if you don't know what local ring means, is not a very helpful definition. But what a local ring is, okay, a local ring is just a ring that has a unique maximal ideal. So, has a unique, and why would we care about that? Ooh, unique. Unique doesn't have a G in it, by the way. I'm not an English major, but pretty sure. Unique maximal ideal. So why would we care about that? Well, if we were going ahead and just taking germs of continuous functions at a point in a topological space, then what this maximal ideal would correspond to would be the evaluation of the point that we're sitting at of all these functions. All these functions, they determine if I took the germ of continuous functions at a point, I couldn't take one of these germ elements and evaluate it somewhere else, because two continuous functions that agree at far enough, if I get close enough to X, might disagree elsewhere. But they do have a well-defined notion of evaluation at that point in general. That's a homomorphism that you can define on them that sends them to whatever, the real numbers or the complex numbers, whatever number field you happen to be taking your continuous functions in at the moment. And so yeah, evaluation at that point, and then the set of all functions which are 0 when you evaluate that point corresponds to that unique maximal ideal. So in a sense, having this unique maximal ideal means that when I talk about the germs of functions at a point, they only see one point. There isn't some phantom other point somewhere that is floating off in the distance that they're having to acknowledge. And this is also...
Unique maximal idea is made of all the non-unit functions.
Exactly, and so now you can think of it as like, it's all the things that vanish here. Okay. So these are the sorts of local ring, or these are the sorts of spaces that we're interested in studying. And now, why don't I go ahead and return to the discussion of classical algebraic geometry just for a bit, because I want to write down lightning quick the construction that I was going over last time, and I didn't quite finish it, I don't think. But the construction is to start with the coordinate algebra for a variety, so it will satisfy A, algebra over a field F. It's finitely generated. And it has no nilpotence. And what we would do, we need to associate a space to this guy. So I need to build a topological space, and in particular, that means I first need to build a set. The set that we go with is XA going to be equal to the set of all subsets J of our algebra, such that J is a maximal ideal. And after having our brief discussion about unique maximal ideals and points, the reason is exactly the same. A maximal ideal, if you're talking about just the continuous functions on a topological space, corresponds to evaluation at a point. So, yeah.
In generality, it doesn't mean...
If we were just talking about a sheaf of sets, then yeah, it would just be a set.
I meant even if it's a sheaf of rings, we're just putting like the equivalence class on them.
Because I didn't talk about the actual ring structure. I waved my hands and said, you can acquire the ring structure by going and zooming down onto open sets where both elements are defined. So if you wanted to multiply or add two sections, two germs whose representatives belonged to different open sections, yeah, you would just zoom down to a W on which they are both defined. There will always be such a thing. Take the intersection of these guys, and then you can just do the operation there. So yeah, there is a ring structure on there. I just didn't say it. You would get it automatically if you just defined it as a colimit over the diagram of open sets. Okay. So yeah, these maximal ideals correspond to all of the functions, for lack of a better term, that are sent to 0 by an evaluation at a point, at least as long as we're talking about continuous functions. And the same is actually true if we're talking about the polynomial functions on a variety. So we just start out with our algebra and go backwards with the same idea in mind, that every single one of these maximal ideals should correspond to an evaluation at a point. So this gives us our set, but then we also need a topology on this guy. So a topology on this, we need to know, so let I be an ideal. We need to know what the collection of closed sets and or what the collection of open sets on this set is supposed to be, because that's what defines a topology. It's equivalent. You could go with open sets, or you could go with closed sets, because obviously you just take the complement of one to get the set of the other. And we're going to generate closed sets on our space here using ideals, just by asking that, so actually VI. VI will be like a prototypical closed set for a given ideal, and it will be the set of all maximal ideals, so J in J in XA, Such that, and now let's think about this. So we have an ideal. We can roughly think about this as corresponding to a collection of functions which all vanish on a given closed set. And I want that point that I'm talking about, that maximal ideal, to belong to that closed set. So if every single function in my I ideal vanishes on this big set, then they also vanish on that point. And so they belong to that maximal ideal. So I subset J. Because every single point in that set vanishes there. So that's what we care about. We care about these closed sets, which are all of the maximal ideals which contain a given ideal. And this is the Zariski topology on this set here that we've derived from an algebra. Okay? And now we have one last thing to talk about. The idea now, and then there's actually one thing worth mentioning. So there is a basis for this topology that's actually quite nice. And it looks like this. So for any element, so if A is an element of our algebra, I can also define a basis from open sets that look like UA is the set of all J in XA, such that now instead of A being contained in our maximal ideals, I want the opposite. I want A is not in our maximal ideal, because it's the complement. It's got to be an open set. So these are open sets, or this is a basis for the open sets. I topologize this set right here with the Zariski topology, who are closed sets that look like this guy. Equivalently, you could take a basis of opens that look like this guy. And it's going to be easier to state the sheaf of rings on this guy in terms of the basis opens that look like this guy. So I'm going to go ahead and do this.
So is V going to be some sort of variety, eventually?
V is the vanishing set of this ideal. That's why I use V. But yeah, no. Technically, this thing is the variety. It's not itself a subset of affine space because we've defined it intrinsically. It's just a topological space with a sheaf of rings. But it is equivalent as a ring space to a subset of affine space that coincides with a variety. So that's the idea, right? A variety is a subset of affine space that has special properties. But this thing is equivalent as a ring space to that sort of thing. It's an intrinsic definition that captures the same notion. Okay. And so now all I need is a sheaf. And if I'm not going to prove that it's a sheaf. I'm just going to show you what the subset, what the open subsets are. Or excuse me, what the evaluation on open subsets are. And then I'm going to ask you to believe me that it does end up being a sheaf. But if you feel like it, you can go and look at it yourself. But the idea is I started with this algebra. And this is the algebra that I want to be the coordinate functions on my space. So somehow, when I take the sheaf for a given open set, I should be hoping that I wind up getting this guy again. So I'll give a really, I'll write, actually I haven't defined, I'll define localization after this, and I'll give a really concrete way that avoids talking about that first then. So for a given element A right here, so I would want to actually, yeah, I can go ahead and just define it for an arbitrary open set. It'll be, when I go and talk about it for schemes, then I'll need this guy. But let U subset be open. Okay. And then, you know what, I might as well just define, I'm going to end up using it anyway. Sorry, going back on things in my head. Let me tell you guys what localization is, because that's going to make me have to say fewer words here. So localization. Yeah, there you go. Localization of a ring. And April already sort of shouted out what it is going to be. It's essentially going to be a field of fractions. So it doesn't necessarily have to wind up with a field every single time. It's just going to be a ring where I've made some more elements invertible. And as a result, yeah, I can sometimes think about them as being written down as fractions. So localization of a ring are with respect to a multiplicatively closed set. This is just typical of when people are presenting localizations, since you're going to end up including as unit elements anything that is a power of something that you turn into a unit element. We take something that's multiplicatively closed just so that we don't, so that that's incorporated into the localization itself. And we also usually ask that these guys contain 1. So they're always non-empty. They contain 1. Obviously, having 1 in there isn't going to hurt anything because asking 1 to be invertible is a non-trivial demand. Huh? That would be a problem. Yeah, as soon as you have 0 in that set, then the only localization is the trivial ring, and it's just the 0 ring. So yeah, if you make 0 invertible, then there's no information left to talk about. Okay, and so we write this down as S inverse on R. And this is also going to be equivalence classes, but not just of elements of R. We want pairs. So R, S, where obviously R is an R and little s is an S. And we want to say that 2 of these pairs are equivalent, that they determine the same element of our localization if there exists, so there exists some element of our set that we're turning into units such that T times the cross, they call it cross-multiplying when you're doing elementary school algebra. But the thing that you would check to make sure that these guys don't represent the same fraction. So RS prime minus R prime S. Right? If these guys were fractions, like Avril mentioned a second ago, and then I just multiplied on the top and multiplied both of them, excuse me, by the common denominator, or by the denominator of each, then I would eliminate all denominators, and I would wind up with this expression right here. And if you were defining rational numbers, that guy would show up as well, because rational numbers are just pairs of rational numbers are pairs of integers, such that this guy is 0 if they're representing the same fraction. So we have the same sort of thing here, except now instead of, this is equal to 0. Now instead of this guy being equal to 0, it might be equal to 0 after you multiply him by an element of S. So he might be a 0 divisor.
Sorry, what was M closed?
M closed, multiplicatively closed. Yes. Yeah, so, and that's just because, you could do it without a multiplicatively closed set, but you know you're going to make anything that you form out of products of units into a unit, so you might as well just include those in the definition anyway. Okay, so this is the idea of a localization, and again, I don't have enough time to go over all of the theory of rings, but when we go ahead and localize with respect to a set like S, then now every single thing in S becomes a unit. We might have additional things that also become units, so like if F is in S, and F is equal to a product H and G, these guys have definitely got to be units when we go to our localization, because, and if I just now multiply by either H or G, the thing that's left over should be an inverse for the other one. But so just because we've enlarged S to get all of the obvious units doesn't mean that it contains all of the new units of my localization. There might be units that are not in S. Okay. Because of this thing that I'm doing right here, where I'm about to use it to describe what it means to go from the set of all elements on A to the elements that are supposed to be on this open set. That's literally the thing that I'm using it for right here. So I can go back right over here and say that the sheaf element defined on this guy, so So f of a, defined on my open set who looks like this, is just the localization of a with respect to this element. And when I go ahead and localize with respect to just an element alone, so localization with respect to just an element of R, we say that that's the same thing as localizing with respect to the set that contains all of the powers and 1 of that. So there we go. That's why it's called localization, because it's literally the algebraic procedure on the algebra construction side that's giving me the restriction of my coordinate functions to this open set U.
So that's why you don't want to That's why you don't want to
Yeah, it was this construction comes from doing algebraic geometry, and so even though you can motivate it purely from the algebraic side of I want to turn things that aren't units into units, it actually has this geometric meaning.
So U of A is the neighborhood containing the element A?
Exactly this basic open of this form. Right. It's the set of all maximal ideals that don't contain my element. Okay. Mm-hmm. So again, and you can think about this, if we're reinterpreting what our maximal ideals are, the maximal ideals are points in our space. Belonging to a maximal ideal means that the evaluation at that point sends you to 0. This is the set of all points that this thing doesn't vanish at. The pre-image of everything but 0, and everything but 0 is an open set, at least when we're talking about normal topology. Okay, so there we go. This very succinctly is our procedure. We start with an algebra. If it satisfies these 3 properties, then going ahead and building a topological space in this way with a sheaf that has these evaluates. Again, I'm not going to prove that it's a sheaf, but it is. It will result in something that is equivalent as a ring space to a variety of an affine space. So that's fantastic. We have a way of starting with our coordinate algebra and winding up with the space that we want to study with it. And so if we're interested, like I said back in the spring, if we're interested in extending the scope of our geometry to all those spaces that we can still study using the tools of commutative ring theory, we now have a really easy way to implement that. We start with any general commutative ring, and then we try to run this exact same procedure on it to wind up with an associated space. It's going to run into an issue, but we can cure that very, very quickly.
Okay, so this construction is given an algebra with no nilpotence, we have a way of constructing a ring space out of this thing, right?
Exactly, yeah. It's got this underlying set, it's got this topology, it's got this sheaf.
And so we're identifying the ring space with what?
Where we could also, there is a variety, there is a subvariety of some affine space that is equivalent as a ring space to this guy. So there is a homeomorphism between their underlying topological spaces that preserves all of their sheaf elements, all of their local sections.
And so this ring space is usually studied in that affine variety?
Exactly, yeah. This is even though it's now an intrinsic definition, so it doesn't have to see it as embedded in an affine space, this is equivalently, morally, it's just an affine variety. And any space that you arrived at in this construction procedure, starting from an algebra which had these properties, would always be an affine variety in affine space over that field. So that's the cool thing about this construction. Okay. So now we're going to try to, it doesn't matter where I should start over here. I should run across the board in a logically coherent manner as much as possible. Okay. So we want to do the exact same thing, but now instead of starting with all of those, are a ring. That's it. And obviously, again, I mean commutative ring with unity. I'm just not going to say all that. Okay. Well, we run into a problem immediately at this level. If I just wanted to go ahead and define spec R in exactly the same. Yeah, now I'm going to call it spec instead of that because that's what we're eventually going to call this is the spectrum of a ring. But if I wanted to find it in the exact same way, so J such that J is a maximal, well, I would, ideal, yes.
Is this notion of spectrum at all connected spectrum functional analysis?
There is a connection between the two of them. I just can't tell you what it is. But yes, there is a connection. You can interpret them as spectrums of linear operators in certain cases. But yeah, I can't detail that because I haven't personally looked into that. But I know that it is possible. Okay. So if we did this, we would want this spec procedure to end up determining a category that goes from our rings, so from the category of rings, to locally ringed spaces. That's what we would want this spec to end up determining. But there's a problem, because there's an obvious thing for me to do to a ring homomorphism, so R and R prime, if I have J a maximal ideal of R prime, there's an obvious thing for me to do if I wanted to make an ideal on R, and that's just to take the preimage.
Local ring or
Local ring spaces.
ring or ring?
Local ringed spaces.
Ring.
Yeah. So this is an ideal. Whoop, and whoop, that shouldn't be an in. There we go. This is an ideal in R. But here's a problem. If this is maximal, this in general is not maximal. Think of the integers embedding into the rational numbers, right? The zero ideal in the rational numbers is maximal. It's a field. But the zero ideal in the integers is definitely not maximal. You can certainly add other things to the zero ideal and still have a proper ideal. Okay, so that sucks because, again, this is the natural choice for what to say spec should do to a function. It should send it to the procedure that does this. Diagrams work out exactly how we want them to if this is how things work.
So, sorry.
No problem.
So spectrum R we're interpreting now as this ring space that you constructed over here, right?
Not yet. No, this is different. Exactly. I have to modify this construction procedure, and it's for this reason right here. Right? If I tried to use this, using this construction procedure with maximal ideals, this works out. This works out over there.
So you haven't said yet how to identify spec of R with a local
No, I haven't. Exactly. I haven't mentioned that yet. No. No. But yeah, if I repeat this exact same exercise over here, it turns out that this works out just fine over there. So I would never needed to make this switch as long as I was studying affine varieties. Using all of their points as just maximal ideals of their coordinate algebra, totally sufficient. As soon as I go to general rings, this is not maximal if this is maximal. And again, I have examples. All right, so what do? Well, this might not be maximal if this is maximal, but if this is maximal, then this is prime. And if this is prime, then this is still prime. So there we go. We just enlarge the scope of what it means to be a point. Instead of being a maximal ideal, now we just ask that ideals are prime ideals, and now the functoriality of this construction is no longer in doubt. So let's go ahead and rewrite everything here. It's going to look very similar, but I'm just going to swap out prime ideals for maximal ideals. So R is a ring.
Yeah, I was just going to ask you, usually spec is defined in prime.
Exactly, yeah, no, and that's the thing. We would like to use maximal ideals, just like we used for varieties, because there is a very clear connection between those things and the points of a space. But we can't, right? It's not an option for us. So what do? We do the next best thing. If I'm forced to include these points whose nature I don't understand well, I just try to include as few of them as possible, and then try to understand that nature afterwards. So R is a ring. Now I change this to spec R.
So I've always had the question, why is the spectrum of the ring defined? Is this the reason why it's defined as
As the prime spectrum? Yeah, the reason why it's defined using the prime ideals is, again, we started out from the construction on a coordinate algebra on a variety, where using the maximal ideals as a one-for-one to the points made perfect sense. And we would like to do that in general because this is the only construction procedure that we know of to take a coordinate algebra and turn it into a space. And it actually doesn't even come from algebra. Grothendieck steals it from functional analysis, which Abril and I have seen now after going through functional analysis with Cobinson. Gelfand and others have preceded Grothendieck's work on doing this in functional analysis. And it's Grothendieck's work in functional analysis which led him to view this construction as a place to start. But he also happens to know enough category theory to know when the universe is telling him that things need to change a little bit. Okay, so we swap out J's here for P's and maximal ideals for prime ideals. P is a prime ideal. We can do the exact same thing here. I just change the names of these guys to be cute. So this guy goes and becomes the spectrum. So this in spec R, such that, oh wait, whoops. That one was correct. It was the other guy. Such that he contains it. And again, it's been a while since we talked about prime ideals, but if you'll recall, the prime ideals of our coordinate algebra before, they corresponded to varieties. So you can think of us having enlarged our notion of what it means to be a point in a space from being just an individual point to now all subvarieties. Okay. So, and then, yeah, this is also primes in our spectrum and doesn't contain prime.
So you're not modifying this construction so that we can associate things to a ring space? Well, what exactly is the local? You still have to check that.
Yes, so that's the thing, and don't force me to do this right now.
Okay.
But yeah, no, it can be shown. You can verify that, and I have to do one last modification here. This becomes P, and this becomes P. Little p, little p, little p, and this becomes P inverse acting on our ring. This guy is our ring. Yeah, all right. So yeah, no, we just choose to localize instead of, we localize along the exact same procedure. We just take an element and we tell him and all of his powers to become units. And obviously that might imply that other things become units, but.
On that line, it says P is an element of P in the true line.
P is, oh, right, P is, this should be, excuse me, should be an element of R. And then probably should be little r, but I'm not going to go and write a whole bunch of little posts. We all get it? So there we go. So this is, the procedure doesn't change very much, right? Right? Like the only thing that really had to move was this right here, but the localization procedure that we used to actually make our open sets, that didn't change really at all. And I haven't mentioned it yet, but you can go ahead and, because you can write a general open set as a union of these guys, you can use inverse limits to represent the section of a general open set as the inverse limit of all of the open sets that make it. I'm not going to write that down, but yeah, this procedure does in fact define the sheaf for all open sets and not just these special ones, which you might be concerned about if you recalled what I mentioned that a sheaf did earlier and said that it gave every open set a ring. Okay, so we won't be able to, we'll probably have to do one last talk to give like a whole bunch of really great examples of what making this transition from varieties to schemes allows us to do. But as just one tiny little toy one today, I'll go ahead and bring up a problem that I indicated existed with our previous coordinate rings, coordinate algebras in the last series of talks, and then talk about how now this perspective on schemes gives us a really easy way to deal with it. So that was the problem of the difference between the varieties x and x squared, where what I mean by right now by the varieties is the things they determine when I set them equal to 0. So if I set x equal to 0, it's pretty obvious what I get. I just get that one point at the origin. But you might also think that if I set x squared equal to 0, that I'd also get that one point at the origin. And in classical algebraic geometry, that was in fact the answer, because varieties don't allow us to encode multiplicities like schemes do. If we were studying classical algebraic geometry, well, for this space, we would just say that its coordinate ring, we would start with the ring of polynomials in the single determinant, and then we would quotient by exactly the polynomial that determines our ideal. Or, in the polynomial that we're trying to solve, but yeah, it determines an ideal, determines a radical ideal.
Well, x is irreducible, so it's
But yeah, in this case, it's also prime, totally prime as well.
prime, yeah, okay.
But all maximal ideals are prime. And this thing is definitely maximal as well. So anyway, yeah, this is what we would arrive at, and clearly this is just the field again. So it makes sense that the coordinate ring at that point, what the coordinates of a single point are just the field, because again, that you've got one point and one choice for where to send that point along your field. Classical algebraic geometry said that we had to give the exact same answer for x squared, because if we went and tried to repeat the exact same procedure, okay, I've got this polynomial that determines my variety. I would like to go and just do this. Oops, shoot. Don't know what I'm doing. But this is not just our field. It's not just going to be our field anymore. Elements of it are going to look like a plus bx, because x is now a nilpotent element. If I square it, he becomes 0. So all of his higher powers vanish. But his first power certainly doesn't vanish. And so I've got 2 coordinates. So this is, as a vector space over F, this thing is 2-dimensional. Well, not having nilpotence, I remember, I told you, was a big deal. We couldn't have the coordinate ring of a variety have nilpotence. And hence, this guy can't be the coordinate ring of a variety, and so classical algebraic geometry had to stop when hitting this guy and say, okay, we abandon him. We go back to this and say that this is the coordinate ring for that guy. And in doing so, you have ignored the multiplicity of this intersection, right? This is a double point. There should be some way of recovering that information. And if you're going to go off and prove a counting theorem in algebra or in algebraic geometry that cares about the multiplicities of intersections, you're going to need your tools in order to be able to record this information. This is not an obstacle for our scheme ring corresponding to this variety, right, or variety, to that scheme. So while these two different polynomials give the same variety in classical algebraic geometry, when I talk about the schemes they determined, which obviously come from this ring and this ring respectively, they are different, because those rings are different. And more importantly, the ring that we associate to x squared there, it records the information that it is a double point, right? It has a 2-dimensional space. Perfect. There's the 2 that I was looking for. If I wanted to use this geometric construction in order to alleviate some counting theorem, then again, if multiplicities show up, if I assume that there are no multiplicities or multiple intersections, I can go ahead and use varieties just fine. But as soon as multiplicities arrive, I'm forced to use schemes, because they are the only thing that can record the information that I need. There's a lot more things that schemes can do. I'll talk next time about the arithmetic genus and how using schemes can give us a way of going from 2 dimensions, where the arithmetic genus was originally discovered, into higher dimensions where the original formula makes no sense. So, with the last 10 minutes, I'll go ahead and wrap up for questions. Go for it. It's an invariant of a variety and more generally a scheme. But yeah, no, so because just like when you're doing the classification problem in topology or just in algebra, right, you have two examples of things and you want to show that they're not isomorphic. In general, going and proving that no isomorphisms exist is a really hard thing to do, but if you have an invariant on which they both differ, then boom, you're all done.
Is it like in some ways like obviously because like to the subspace variety that's actually genus and topology?
It does bear a relationship to the topology. What really makes it related to the topological genus is how they're calculated looks practically identical. Once you know about sheaves and schemes, then we can talk about this thing called sheaf cohomology, and I can write them down in a way that makes them look indistinguishable. You couldn't tell the difference between the two.
Because the idea is that obviously the varieties associated to the polynomial because of multiplicity, so then we use this.
Yeah, if we're trying to do some sort of theorem that counts multiplicities or counts the number of times something happens at an intersection point, then it might need to care about the degree of that intersection.
Just so in general, I think I'm not saying is in general, like if I had another polynomial that had like the dimension of that vector space would correspond to.
Yeah, exactly. You would wind up with enough directions in that space to count.
And how does it count? Let's say you have like multiple roots, different roots, and each one having their own multiplicities.
It will be, yeah, no, exactly. You decompose space into these spaces that look like individual normal points like you're used to, and then these special double points or triple points or higher order points. So like instead of having a space being like a bunch of discrete points that are just points that all have the same character, some points are special. They're double or triple or something like that.
And so the next talk is going to be about more.
I'm going to talk about, applications, why schemes. Now that we have seen how we arrived at the construction of a scheme. By the way, this is an affine scheme. I'll talk about general schemes maybe briefly, but it's just something that locally looks like one of these guys. So every single one of these that we've talked about are like the basic objects that all general schemes are made of, but they are all made in the exact same way. They're just spectrums of rings, which are the sets of prime ideals, given the Zariski topology and then given their associated sheaves. And yeah, so next time I'll talk about arithmetic genus. And, yep.
Very brief, I will expand on that next time, but very briefly now, on a general matter. Overall, from the classical point of view, as a technology, which is, of course, the interplay between algebraic issues in the base field, like, say, even a finite field, then a polynomial also. Then you look at the geometric solution space. So you have a geometric entity, the solution space associated algebraic entity, the pressure, for example. In classical algebraic geometry, the interplay was like go back and forth.
Yes.
And of course, generalizing not arbitrary fields or something like that, beyond your there's a substantial generalization. The expectations for example, is that if we have, let's say, an expression like x squared plus y squared plus z squared plus 1 or something like that, that might behave like the sphere or something like that. In other words, some expectation is geometric. Now, that was the classical point. All these formalizations in the last few decades, have they facilitated considerably this interplay into realizing the expand between the algebraic? It's polynomial, let's say.
Yeah, well, absolutely, because we now have, there are tools of commutative algebra, commutative ring theory, that you just don't get to use on the, I have the list of properties that algebras over varieties satisfied, but there are invariants that are all just trivial on them, that therefore don't have any sort of geometric instantiation when you push using this functor, the spec functor, to the other side, as long as you were talking about varieties. Now when you talk about schemes, invariants that were trivial before become non-trivial also on the geometric side, so you get to see new geometry, richer geometry than you would have seen with varieties, which is hopefully to be expected when you generalize something. But yes, you can.
Expand this point of the class.
Absolutely, and just as in the classical case where algebraic geometry was especially concerned with taking a geometric problem that was hard to solve and turning it into an algebraic problem that was easy to solve and vice versa. Exactly, this interplay is still taking place nowadays. But we have, if you know category theory, they make it lots easier. They make it much shorter, much briefer than anything in the classical situation ever would be. The difference is, the motivations for the definitions become less transparent, but each of the proofs becomes much more conceptual and transparent. So that is, there's no free lunch, right? You got to do some conceptual hard work somewhere, but all of that hard work gets moved onto the definitions, and the proofs generally end up being much more conceptual. A great example of this for something that happens in analysis that's far removed from algebra and category theory is how Gelfand uses the theory of commutative Banach algebras to reprove Wiener's theorem, the Wiener-Tuberian results, is the exact same idea of, okay, I have this very interesting result, the Wiener lemma, but its proof is not very transparent. It's not very obvious why it's true. Wiener was just a genius to figure it out. And so Gelfand comes back with the theory of commutative Banach algebras, which is substantial. You have a lot of definitions that you have to understand. But in understanding those definitions, you require a proof of Wiener's lemma, which is very conceptual. It really explains why Wiener's lemma is true. And this is the exact same sort of thing that's going on here, hopefully. Thank you.
Wiener's lemma is that inverse function.
Exactly.